Yes, hi there. Hello from the Netherlands. Let me share my screen for a moment. So I guess this is okay. So now you should have a presentation. So welcome to Cryptography 101 for Java developers. So I'm Michel Schudel. I'm from the Netherlands. I work for a software company called Craftsman. So we have a lot of consultants doing all kinds of interesting IoT stuff. And we work at a variety of clients. So namely the Rabobank is the bank where I'm working for. The Dutch Railways, bol.com, which is a big retailer in the Netherlands, Dutch ING, and also Dutch IRS. And you can reach me at Michel Schudel on Twitter. So if you're interested in my tech ramblings, please follow me. And of course, you can email me as well. So to get right into it, why this talk? Well, I was really into Bitcoin, Ripple, Ethereum, those kind of crypto coins. And I was very amazed because you basically log into a exchange site, and then you go into HTTPS and you do some transactions. And you see them in the blockchain. I thought, well, what's all making this tick? So basically, there's a lot of cryptography underneath, and I became interested in that. And it's a niche I think not a lot of developers have on their minds all the time, me included. But it's good to know some stuff about it in case something, for example, goes wrong in your HTTPS connection or whatever. So I hope this is a nice introduction to cryptography and how it's done in Java. So that's what I want to give you today, a basic understanding of cryptographic concepts and how they're done in Java. So let's go into it. So what is cryptography actually? Well, this is the definition you find on Wikipedia. And it's basically the practice and study of hiding information. And it's been going around for a long time as well. So if anybody knows what this is the Rosetta Stone, which contains a part hieroglyph Egyptian and a part Greek, which enabled us to basically decrypt these hieroglyphs. So this was uncovered in 1799, I think. The Romans used something like encryption as well. So a simple cipher, so just basically letter replacement. So each letter shifted by 2, and every platoon or garrison chose a different shift. So that was basically a very simple encryption. And you might be interested to know that in the Kama Sutra, there is also a passage concerning encryption as a means of exchanging secret messages between two lovers. So if you thought encryption is not a sexy subject, I just proved you wrong, okay? And of course, this one, the Enigma machine, which probably a lot of you know, used by the Germans in the Second World War to basically encrypt messages. And it was believed to be decrypted by Alan Turing and his team, but I learned on a Polish convention, actually, that is actually 2 Polish scientists who learned to decrypt it a few years earlier. So I will give credit to them because they were the first ones. So let's dive into it. What does cryptography solve? 3 problems. The first problem is confidentiality. So basically making sure no one can read your data or messages. The second one is integrity. So making sure the message you actually sent has not changed by anyone during transit. And the third one is authenticity. So I can say, yeah, I'm Michel Schudel and I sent this message to you, but actually, am I who I really say I am? So you have to prove that. So we'll look at these 3 things today. And some key components of cryptography you have to know. So first, you have some data, of course, that you want to encrypt or decrypt. Second one is the algorithm. So you have to have some process into which to encrypt and decrypt the data. But of course, you need keys as well, because it's like basically putting something secret inside a vault and you don't have a key for the vault. So, the vault, how the vault works, everybody knows. How the algorithm works, everybody knows. But you still need to have a key that is specific for you, so only you and the other person can encrypt or decrypt this message. So these are the 3 key components that are used in modern cryptography. So modern cryptography or contemporary cryptography basically consists of 3 parts, or 3 kinds, so to say. So on one hand, you have semantic encryption, where Bob and Alice use one shared secret key to encrypt and decrypt messages. And the other one is asymmetric encryption, where basically there are two keys. And if, for example, Bob wants to send a secret message to Alice, he will use Alice's public key to encrypt the message, and Alice will use her private key to decrypt the message. So these keys are complementary. You can only use one key to encrypt the message that was to decrypt the message that was encrypted by the other key, and vice versa. So that's asymmetric. And the third part is basically hashing, where you have a piece of data, you put it through a hash function, and out comes a fixed length byte array that is basically like a signature or a stamp of your original data. And we're also going to look at that in a moment. So these are three key components of contemporary cryptography. So how do you do this in Java? Well, Java has basically two APIs, the JCA and the JCE. The original idea was that the JCA was an interface and the JCE was an implementation, but actually through the years this has kind of have been mixed a little bit, and now people talk about JCA, JCE in one go. So they're basically the same thing, especially for end users. So what does this look like? Well, if you have a Java application using cryptographic functions, you can basically say, okay, I have a request to the JCA, JCE. You go through the API, and then you have one or more CSPs or cryptographic service providers. So the Sun JCE is already included in the JDK, so it contains already a lot of cryptographic functions. But if you really want to do advanced stuff, or maybe different stuff that is not included, you can plug in just any cryptographic service provider you want. For example, Bouncy Castle is a really well-known one. You can find it on www.bouncycastle.org, or you can use another CSP that you can plug in. So then the question is, of course, how do you plug in a CSP or cryptographic service provider? Well, that's really easy. There's a security class in Java that has a static method called addProvider, and there you can just plug in the class that represents your security provider. So it's really easy. So if you don't want to do this programmatically, you can also register it in the java.security file. So for example, in this case, at number 3, I have this Bouncy Castle provider plugged in. Word of notion, the order is important. So if a function is found in the first provider, but also in the third, it will always take the first. So if you really want to have the third, you can force it programmatically, or you have to put it on top. Okay. So in JDK 8 and previous, you had to update Java security in this location, and then place the provider jar in lib.x. So this is the library extension mechanism. Well, this has been dropped in JDK 9 and onwards. So now you just have to put the jar in the class path, and also the Java security file is on a different path, as you can see here. So just a little bit information. It's a little bit different from JDK 9 and onwards. Okay. So these are a few of the classes that are in the JCA, JCE. I'm not going to go through them now because we'll encounter them in this presentation, but just to give an indication, this is basically the stuff you're going to use. So it's not that big. So it's not too complex. So today we're going to cover hashing, semantic encryption, asymmetric encryption. We're going to look at digital signatures, and we're going to look at certificates. So we'll go through these one by one. So let's start with hashing. So hashing is basically, you take a piece of plain text, you put it through a hash function, and out comes a hashed text, which is basically a fixed byte array. And it has a few interesting properties. So the obvious thing is it's one way. So when you have the digest or hash, you cannot reverse this and get back the original data, because it's basically a stamp and not actually lossless encryption or decryption. It's deterministic. So if you put in the same piece of data, out comes the exact same digest. It's fixed size. So no matter how big your data is, the digest is always the same size, depending on the type of hash function you use, of course. It's pseudo-random. So for example, I've changed one character here, so a V to a U, and out comes a completely different digest. So there's no way to see a pattern in this. That's really important, for example, in Bitcoin mining, which we're going to look at in a moment. So what algorithms are there? Well, you probably heard of these, MD5 and SHA-1. but don't use these anymore because there are already collisions, and it's not safe to use them because you can have two different pieces of data that will give you the same hash. So don't use this. There's also SHA-256, which we're going to look at in an example, which is still secure, but I would recommend you use SHA-512 or something like that. That's safer. So how do you do this in Java? Really simple. There is a class called MessageDigest, which contains a static method getInstance, which you provide the hashing algorithm to. Then you will get a MessageDigest class. It has a digest method you can put in your data, and out comes a hash. But it's easier if I just show you, would be my best guess. So I hope everyone can see this, otherwise I will hear. This is the MessageDigest, as I just told you. I have a piece of input here. It's called S, and I have to look at where is S. Oh yeah, I have pieces of data here. Then I will call the digest method on the MessageDigest. Out comes a byte array, and then I print out some stuff. So I will just run this and show you what happens. So there it is. So this was the first one. So piece of data, out comes a hash. It's one way only. It's deterministic. So I put in the same piece of data here, and out comes the exact same hash. It's pseudo-random. So I changed one letter here. So you see out the digest is completely different from the one above. So it's pseudo-random. And it's fixed length. So I have a lot more data here, but the digest is still the same size, as you can see. So there was a small demo. And an application of hashing is, for example, in Bitcoin block mining. So you can see here the Bitcoin energy consumption relative to several countries. And it's like 90 or 95% of the energy consumption of the Czech Republic. And this was like a year ago. And it only got worse since then. Why is this? This is because of Bitcoin block mining. So there's an agreement in the Bitcoin blockchain network that a hash of a block should start with 4 zeros. So a block is just a piece of data. So for example, a block contains a few transactions. So for example, I will give some coins from my to JFO conference and also to DevDays. And this transaction is a block, and now I want to create a hash of this block. So I put it through a hash function, and out comes a hash. But it doesn't start with 4 zeros. So how do I change this? Well, there's something called a nonce in each block. And of course, I cannot change the transactions because that would be crazy. But I still have this nonce character I can change. So I will increment it by 1, and I'll put it through the hash function again. Because the data is now different, the hash function will give me a completely different hash. So it doesn't start with 4 zeros again, so I will increase the nonce again to 2 and put it to the hash function again. Now it started with 4 zeros. So this is a valid block in the blockchain. Now, of course, this only took me like 3 iterations, but of course, in reality, this will take, well, quite a little bit more than that, even so that mining a block takes a lot of consumption because you have to go through this hash function again and again. You cannot predict anything when it will start with 4 zeros, so that's a pseudo-random part. Basically, this is why this takes so much energy. So that was hashing. So let's go to semantic encryption. I already showed you semantic encryption is basically Bob and Alice sharing a secret key. Bob uses this key to encrypt a message, and Alice will use it to decrypt the message again. So for example, I would have the text called DevDays, and it's plain text. I will put it through the encryption algorithm. It needs a key, of course, and it will give me a piece of encrypted text. There are a lot of semantic encryption algorithms, but the most famous one right now that most people use is AES, Advanced Encryption Standard. It was created by Vincent Rijmen and Johan Dame here, 2 Belgian cryptographers. And it's basically the encryption standard that goes on in, for example, HTTPS handshake today. So we're going to look at the example of that in a few moments. So how do you do this in Java? Well, it starts again with a static method. So there's a class called key generator that you can call get instance on with the encryption algorithm you want, in this case AES. you get a key generator back, and then you can say, okay, give me a key, because now I need a key. And you only have to specify the key size. So it's like 128, 192, and another one I can't remember. Then you can go to the class Cipher, do a get instance on that. So that will basically give you the algorithm. You will initialize this with a key, and then you will say, okay, here's my piece of data, and there's a little cryptic method called doFinal, which basically allows you to put in the data. There are also update methods on this, but I will not go into that today. And out comes a piece of encrypted text. So I will give you a short demo of that. So let's see. Yeah, it's this one. So what I told you, you have a key generator that you call a static instance on. Then I say, okay, initialize it with key size 192 and give me a key. So I will print this key for informational purposes. Then I will create a string. It's called DevDays. It's 8 characters. Remember this. And it repeats itself 16 times. So this is a new method that was introduced in, I think, Java 11 or something. Then I will go to a Cipher class. I will get an instance. This will be important in a moment, so remember this. And this is a piece of padding, which basically specifies, if your string is not exactly bits of 8, then I will pad some zeros or something to the end. So that's you can specify how the encryption algorithm should do this. You put the Cipher in encrypt mode because it is used for both encryption and decryption. And I will take the input, which was this string, and I will encrypt it, and out comes an encrypted output. And on the other hand, I will decrypt it as well. So I will initialize it in decrypt mode, put the encrypted output in there, and out should come the original text, hopefully. So if I run this, you see the repeating string. You see the key here for information purposes. It's 192 bits. And you see the repeating string here. And here you see the ciphertext. So, well, it looks very nice, but if you spot closely, there is a repeating pattern here. See, so you see 137E3 and starts again here again. So why is this? Well, it has to do with the ECB or electronic copybook encryption I just specified in the string. So what it basically does is semantic encryption does it in chunks of 8 bytes. And if you use UTF-8 in text, you have exactly 8 bytes in DevDays. So it will take the first 8 characters, encrypt them, the next second 8 characters, encrypt them, etc., etc. So you get a repetition. So you might ask yourself, is this really important or really dangerous? Well, if you look at it from a textual point of view, maybe not. But for example, if you were to encrypt a picture, you would end up with something like this. So it's still visible what the original picture was. So basically, this is a pattern, and a pattern is always ground for an attack vector on a hacker site. So we have to do something to fix this. So thankfully we can, because there's something else next to ECB. There's also CBC or Cipher blockchaining. So that basically works a little bit different. You start with an initialization vector, which is a random piece of data. You feed it into the algorithm and the plain text, and the resulting ciphertext will be used as the initialization vector for the next piece of data. So in this case, every time the ciphertext changes, and there's no concern about pattern anymore. So if you were to put it through a picture, you would end up with something like this. It is similar to semantic encryption without an initialization vector, but anyway, this is the difference. So next to key generator, you also have secure random class. You ask you call the static method get instance, and you say, I want to have a random piece of data with next bytes. Then you get the Cipher class, you put both of them in instead of only the key, and out comes the ciphertext. So this is all business as usual. So if I were to show you that, so the code is basically the same, but you have actually a random piece of data here, secure random. So you get the next few bytes from that. So it works like a generator. And then you create something called an IV parameter spec, which is basically a wrapper around this random piece of data. And then you, when you encrypt, you initialize the cipher with the key and the IV, so both of them. And the rest is basically the same. So if you run this, you see it is actually nice ciphertext, but now there's no pattern anymore. So you cannot find this 039 anywhere. So this is completely, the entropy, as they call it, is way better than the previous one. So my recommendation is never use ACB, but always use cipher blockchaining or something similar, something with an IV factor. So then there's the problem of key exchange. So I already showed you it's a secret key. It's used on both sides. So how do you get that across to the other party without anyone noticing? Well, you could put it in a diplomatic bag or a suitcase or whatever, but that doesn't really work over the internet. So thankfully, these two guys, Martin Hellman and Wilfried Diffie, found a really elegant way to actually do this. And it's called Diffie-Hellman key exchange. And it works something like this. So for example, you have Alice and Bob. Well, maybe not the Alice and Bob you were expecting, but hey, well, let's go with it. Alice and Bob think of two numbers, a prime number and a generator of P, which are all in the public cloud. So everything that is here in the middle is accessible by anyone. Then Alice and Bob each think of a secret number that they will never exchange to anyone else. And they will calculate a public number using the two numbers before. So that will be actually a public key, as we call it. So the public key of Alice is 2 and the public key of Bob is 9. They will exchange this over the internet and anyone can read it, no problem whatsoever. And they will use each other's public keys and their own private keys to basically share a secret. And the nice thing of this is, if you use this function, it's a mod, if you calculate it like this, they will always end up with the same shared secret. So they now both have a secret key without ever having exchanged it, actually. So this is a very nice algorithm, and it's used in HTTPS all the time, and it's called Diffie-Hellman key exchange, basically. So of course, the actual function is a little bit more complicated than this, but this is the general principle of how you can share secret keys over an unsecured channel. So it's very elegant. So that was symmetric encryption. And of course, because we talked about private and public keys here, we just go to asymmetric encryption. So let's look at that. So as I told you, in asymmetric encryption, you actually need two keys. One is a private key and the other one is a public key that anyone can share. So if Bob wants to encrypt a message, he uses Alice's public key to encrypt it. And Alice uses his private key to decrypt it. And why is it this way, not the other way around? Because you want to make sure only Alice can read the message, right? Because if I were to encrypt something with my own public key, private key, and I would give the public key to the public, so the decrypted, anyone can read it, and that's no use. So in encryption, it's always asymmetric encryption. It's always like this. In digital signatures, it's the other way around, as we'll see in a moment. These are a few public key algorithms. So Diffie-Hellman key agreement protocol you already seen. RSA is very a well-known asymmetric algorithm. And there's also elliptic curve, which is used in modern HTTPS connections today. So how do you do asymmetric cryptography in Java? Well, you start with a key again, except this one is a key pair because you need two right now. So you have a key pair generator. The rest is more or less the same. So you generate a key pair, which is basically a wrapper around two keys, one public, one private. Then you get the Cipher class again. You call a static instance. It's called Cipher. You initialize it with your public key in this case. So the algorithm works on the public key of this key pair. You put through your message and out comes a ciphertext. And to decrypt it, you use the other key from the key pair, namely the private key, and you do final with the encrypted ciphertext, and out comes my message. So the only difference between symmetric and asymmetric cryptography in this case is that you have two keys and you need one key to encrypt and the other one to decrypt. So I will give a, let's see if I'm out of time already. No, I will give a short demo of that. So I have, let's see, asymmetric encryption demo, where I have a key pair generator here. I generate a key pair. You see the key size is quite bigger because asymmetric encryption works a little bit differently. I will print them out. I have a Lord of the Rings here, so a little bit of plain text. Then I will get the cipher. I will initialize it with a private key. Well, this is the other way around, but for the demo, it doesn't really matter. And I print it out, encrypt it, and then I will put the cipher in decrypt mode with a public key, and I should hopefully end up with the original text. So run this. And it does. So here is the original text. Here is the cipher text, quite a lot bigger, as you can see. And here's the original text again. Now, I also have a demo where I read in the entire Lord of the Rings from the basically the class path. It's I think it's somewhere here. Large file.txt. So this contains all of the text of Lord of the Rings, and you will get an error because it says data must not be longer than 117 bytes. So why is this? It basically has to do that asymmetric encryption is not really suitable for encrypting large blocks of data because of its mathematical structure and because it's way slower than symmetric encryption. So don't use that for encrypting large blocks of data, but you can use it for generating symmetric keys, as we've just seen with the Bob and Alice picture. Use it to encrypt or decrypt symmetric keys because symmetric keys are not that big. Or you can use it encrypting hashes or message digests. And basically, this is where digital signatures come in. So this is a application basically of asymmetric encryption. So we're going to look at that right now. So what is a digital signature? Well, basically, it solves our second part, which we've now seen is confidentiality. So how do you encrypt stuff? Now let's look at integrity. So can we make sure the message has not been changed? That's where digital signatures come in. So basically what happens, Bob sends a message to Alice and totally unencrypted. And this, of course, gives an opportunity to a hacker to intercept this message and change the message. So you don't want this. So you could include a hash to say, all right, this is the hash of the message. You can check if this hash is actually okay. But of course, the hacker can change this hash as well. So you don't really, you don't solve that anything by that. So how do you have to solve this? Well, what you can do is create a hash that has been signed with a private key. So you can actually calculate the hash. So how does this work? For example, Bob has a piece of data and he will calculate the hash of this piece of data. He will then proceed to encrypt this hash using his own private key. And in this case, it's not a public key, but a private key because Bob wants to make sure that anyone can verify the integrity of the message. Then he will make a message that includes the data, the encrypted hash, and the public key. So basically the public key that comes out of his certificate, which we will look at in a moment. And this will basically create a digitally signed message. So Alice will pick up this message. She will validate if this key is actually from Bob through the certificates, as we will see in a few moments. And then she will do two things. She will take the piece of data and she will take the signature, which is encrypted. She will then proceed. She will then calculate the hash of the data herself because the algorithm is actually in the public key information. In the digital signature information. And then she will decrypt the signature using the public key that is in the message. So she will end up with two hashes. And if these hashes match up, you are sure that the message has not been tampered with. So I hope that makes sense. Any questions I will answer at the end. So basically, this is a way to make sure the message has not been tampered with because Bob is the only one who could have signed this message. So how does this work in Java? Well, basically, a little bit like asymmetric encryption, you again start with a key pair generator. You generate a key pair, and then you go to the signature class, and you will call the instance method on that. So in this case, RSA as the encryption algorithm. You initialize the signature with your private key, in this case, not your public key. You will put in your message and you will say sign, and out comes a fixed length of bytes, which is basically your signature. Again, if you want to verify the signature, you initialize the signature class with key pair get public, and then you call a method called update on that to put in the message, because now you don't have an encrypted piece of data, but just the message. And you say, okay, verify this, and out comes a Boolean true or false if the signature is actually correct. So nothing else comes out of it, because that would be information leaking. So I'll give you a quick demo of that as well. So if I would say, let's see, there's a signing demo here. So I will start with a key pair generator again. I will initialize it. I will get a key pair. I will print out the private and public key. I have a piece of data here, which I want to sign. Then I will go to the signature class to say, okay, give me RSA and the hash I want to use to encrypt the hash I want to use to hash the message is SHA-256. And then I will put the private key in there to say, okay, I'm going to initialize the signing. Then I will call the update methods with the data, so the bytes string of the data, and out comes the signature. So if you want to do verification on the other end, you have some received data here. So in this case, it's the same, as you can see. I will get the same signature, and then I will put the algorithm in verify mode with the public key. I will update the data, so I will put in the data in the algorithm, and I will ask, okay, this is the signature I received. So given the signature and this piece of data, do the match up. So out comes a Boolean, basically. And if it matches, it matches. So if I run this, well, you see everything lines up. So the signature matches in this case. So if I were to tamper with this message, so let's see, let's say make this Xbox, for example. So you spell it like this. So now the message has been tampered with, right? So if I run this, you will see the signature doesn't match up anymore. So you know the message has been tampered with. So by the way, all this demo stuff is also available on my public GitHub, which I will give you a link at the end. Okay. So this is basically a short demo of signing messages. So what is an application for this? Well, for example, it's used heavily in crypto transactions, for example. So for example, I would have a transaction from Alice to Bob with the value 100. I will sign this piece of transactions using a private key, and I will send a copy of my public key along with the signature into the Bitcoin, into the blockchain network. So this could be Bitcoin or Ethereum or something else. And then the network can basically verify that the signature is actually correct, because it will take the public key and the signature, calculate the hash of the transactions, and if they match up, the transaction is authenticated, you are sure that Alice is actually the one who initiated the transaction. So this is an application of signing of digital signatures, which, for example, used in signing crypto transactions. So then on to the last part, and I see I'm still on time. That's good. Let's talk a little bit about certificates. So we've covered now confidentiality and integrity, but not authenticity. So is the person who actually sent the message actually the person I had in mind? So that's where certificates come in. So basically, certificates is like a stamp or a piece of data where actually a authority called a certificate authority, or CA, actually has checked my credentials and states that I, Michel Schudel from Craftsman, Utrecht in the Netherlands, is who he or she claims to be, and her public key is this and this. So I've sent my public key to the certificate authority already. And they will sign this using their private key. So I'm sure that actually the person who checked my credentials is actually this certificate authority who's trusted. Well, If he's actually trusted, we'll get in a moment, but this is the basic setup of a certificate. So how do I trust this certificate authority? Well, I'll skip this. They've gone through the same process. So basically, there is a certificate of the certificate authority, and they also have been checked by something called master cert, which is another certificate authority. So they state that DigiCert, who assigned my certificate, actually also is who or she claims to be, and the public key of this certificate authority is listed here below. So, well, you can imagine this goes on and on until you come to this authority called master cert, which is at the end of the chain. And well, the chain has to stop somewhere, right? So this master cert is basically a root certificate authority, which are only, well, there are dozens, but not that much. And they actually have a self-signed certificate, as you can see here. So master cert says, yeah, I see that master cert is actually who he or she claims to be. So basically, that certificate is self-signed, and that basically means that we implicitly or explicitly, I can never remember which is which, implicitly, everybody implicitly trusts this master cert organization because they're a root certificate authority. So yeah, what happens when a problem were to arise with this root certificate authority? So we cannot trust them anymore. Well, actually, this happened in the Netherlands in 2007. There was a root certificate authority called DigiNotar, and basically they got hacked, and a hacker got the ability to basically sign certificates on their behalf, while they did not actually do that themselves. So they couldn't be trusted anymore, but because of this chain, all certificates that were in this chain that they ever gave to basically their clients could not be trusted anymore as well. Well, thankfully, like only 95% of all government certificates on websites was from this DigiNotar. So that was very unfortunate. And basically the government websites were like, well, down for a few days, but it could have been much worse. But of course, this root certificate authority went bankrupt in like a few months because nobody trusted them anymore. So while this is a good system, it's still a little bit brittle because you have the root CA self-signed, well, I wouldn't call it problem, but property. So yeah, so that's basically a little bit about how certificates work. Then the last part is what I wanted to talk about is storing key and certificate material. So you've seen a few demos from me, but they're all in memory, right? So I generated keys on the fly. So if you want to reuse keys, you have to store them somewhere. So thankfully, the JCA API has something for this, and it's called the key store API. And it's basically either an abstract class or an interface. I can't directly remember, but it has a few methods. For example, get key, get certificates, store certificates. So basically, the normally CRUD-like operations you would have in a key store to generate stuff. To generate stuff and to store stuff. And it has different implementations. So the original key store was JKS, but it didn't support symmetric keys and symmetric encryption. So there was an extension of that, which called the JCE key store. But now in latest JDKs, you have the, as a standard, I think the PKCS12 key store, which supports both. But if you want to plug in a different thing, for example, hardware key store, they also exist. So like a big, basically Iron Desktop-like box where you can use to protect your keys in hardware. You can also plug that in. And basically, the class you get is basically a driver for this piece of hardware. So, but thankfully, you don't have to talk to these things directly. So you can just use the key store API. And these are a few examples. So for example, you would get a key store instance. That's a little bit confusing the first time you use it because you first have to use specify the key store you want, and then you still have to load the data. So there's a load method on that, which takes an input stream and a key store passwords. And if it has been loaded, you can do operations on the key store. So for example, if you want to get a key from that, it's basically like a table of what do you call it, aliases and then the key material. So the key is an alias, which is a string, and you need also a password, and then you can get back the key. But there's also operations, for example, for certificates, so you can get and store certificates in this key store as well. So for example, in this case, given an alias, I can call the method get certificate, and out comes a certificate, and I can do with it whatever I want. Now, you can do this programmatically, but thankfully there's also a tool called Key Tool, which is included in each JDK. Well, it's called XA here because I'm on Windows. And yeah, these are just a couple of examples of commands you can use. So for example, to generate a key pair, which you can only use using Key Tool, you can use the command above, which basically says, okay, I want to generate a key, and the key algorithm is RSA. The alias is self-signed, but it could be anything, so it's just a key name. The key store is JKS. The store password is passwords. The validity of this key is 360 days because it already creates like a certificate fingerprint, and key size is 2048. And you can also, so basically what this does is what I showed you in the demo. So basically calling this key pair generator and then also store it in this key store. You can also list the contents of the key store by using list. You can use it to generate a certificate request, which I haven't got time for, I'm sorry. And you can also use it, for example, the last example, to export a certificate if you want. So Key Tool is very handy, and if you want to work with key store material, basically in Java, you use it all the time. So that was the last part. So that was about certificates. One last thing I wanted to show you is basically where all these concepts I've talked about in today come together. Well, that's basically in the HTTPS handshake. So if you connect to a site using HTTPS, you will see all these things. So very quick roundup. So for example, when a server says hello to a client, it says, okay, I have these algorithms for you. So for example, Diffie-Hellman or RSA. So that's basically specifying how we're going to exchange keys and what algorithm. Then the server will send its certificates. The client will verify the certificate using its digital signature. Then it will proceed to use the signature to encrypt basically a common number for both to create a symmetric key. So this is Diffie-Hellman key exchange basically. It will, then the server will decrypt with a private key. So they both have the same number, and they both start to generate symmetric keys using Diffie-Hellman key exchange. After they've generated symmetric keys, because I already told you asymmetric encryption is not really suited for exchanging or encrypting large blocks of data. They use symmetric encryption for that. So they both generate symmetric key, which is the same on both ends. And then we will use AES with this symmetric key to exchange messages. So everything I talked to you about today, you can find back in the HTTPS handshake. So I think my time is almost up. I will try to answer any questions in the chat in a moment. What I wanted to do for you today was give you a basic understanding of cryptographic concepts and how they're done in Java. So I hope I succeeded in that and you learn a little bit about that. And Q&A I will do in a moment. And if you want to play with the demo yourself, you can go to GitHub, to my account, to download the crypto demo, and you will get back all the demos I just showed you and a few more. And please follow me on Twitter. So don't forget to rate my session. I will now I have only 1 minute left. I'm going to wrap up and I'll try to answer any questions in the Q&A. So thank you very much, and I'll see you next time. So enjoy the conference. And let's see, no questions yet. I think there's no question. Please, okay. If you have any questions that you think of afterwards, please let me know and I'll try to answer them, okay? So thanks very much.